Welcome to Session 2 on electrical noise coupling mechanisms. What I'm going to show you in this session is that I believe we can describe all electrical noise problems in terms of four basic coupling mechanisms: conductive, electromagnetic wave, magnetic fields, and electric fields. Now, the way most people describe noise problems is they say, well, you're going to have trouble with fluorescent lights, arcing relay contacts, electrostatic discharge, noise coming in on the AC power line, people with RF transmitters. If you look at noise coupling problems from that kind of perspective, it looks like there's an unlimited, almost infinite list of different kinds of problems. But in this session, we're going to try to boil down electrical noise coupling problems into four basic mechanisms. Before we get to that, though, let's cover a few more basic items. Electrical interference. My definition is it's just unwanted electrical energy with sufficient intensity that it can cause a problem. I don't particularly describe interference or divide it up into man-made noise versus cosmic noise, or periodic noise versus non-periodic noise. However, I don't have any objection to those kind of subdivisions, but I find that a very simple definition, you get electrical energy someplace you don't want it to get to with enough intensity to be a problem. We'll call that electrical interference. Any situation that results in that. Now, every noise problem has three basic parts. There's the interference source, the energy coupling mechanism, which we're concentrating on primarily in this session, and the susceptible system. The most critical part to this problem, I believe, as far as diagnosing and fixing the problem, is determining the energy coupling mechanism. If we know what that mechanism is, and we know where that process is located physically, then we have a very good chance of fixing the problem. If we have no idea how the energy which originated at this location, how that electrical energy got to this location, we have no idea about that, then I think we're going to be in a lot of trouble when it comes to fixing the problem. Then we're going to be working more or less in the trial and error mode. Now, I have to do that some myself. After I exhaust all what I think of as logical diagnostic processes, if they don't lead me to any conclusion, then I'll just try whatever I can think of to identify what the problem is. But I do believe there's a pretty good logical procedure for diagnosing problems, and we want to show you that in this session, or at least start on that here. And it's based primarily on understanding that there are four basic energy coupling mechanisms. Now, sometimes we try to solve the problem at the source. What would you think is a characteristic of the source which would help you identify which source you're dealing with? Well, it's probably the frequency, right? If I told you we were having a 60 hertz coupling problem, well, then here in the U.S. we would know it's something power line related. Maybe in other countries it would be a 50 hertz power line problem. But if we know the frequency, then very often we can use that to identify the interfering source. And that's very helpful. Maybe we can solve the problem at the source. But as I've already said, most of the time we're going to try to do something about the coupling mechanism, so that's what we're going to concentrate on identifying, is the coupling mechanism. Here's a couple of simple examples. Let's say we have electrostatic discharge, which is coming from our finger because we have touched a connector pin, an exposed connector pin, and this electrostatic discharge has gone from our finger through the pin, which is a conductor, through a wire, onto a circuit board where it's actually damaged an integrated circuit. Again, if interference damages the circuit or simply resets the circuit, I still lump those into one broad category of interference. But in this case, we have the electrostatically stored energy, that's the noise source. The conductive path, the finger and the wire and so forth, is the coupling path, it's the conductor. And the circuit that was susceptible was the integrated IC chip. Another example might be high-speed digital harmonics. If those high frequencies get unintentionally coupled to long cables that might serve as antennas, then we can have electromagnetic wave radiation. And that electromagnetic wave might be picked up by a receiver, such as an FM radio, and be an interference problem. Again, we have the three basic parts. The noise source, which you can probably identify from the clock harmonic frequencies. The electromagnetic wave coupling, which is one of our four possible coupling mechanisms. and the susceptible circuit. We'll always see that problems can be divided into these three basic parts. Also, we have two concerns about noise. Sometimes we're worried about an electronic system being susceptible to incoming electromagnetic energy, and other times we're concerned about the system unintentionally emitting electromagnetic energy of some kind. These two problems tend to go together, don't they? If an antenna can transmit, that same antenna can receive. So we think of as susceptibility problems and emission problems as, generally speaking, having some link between the two. If a system is bad with regard to emissions, there's a very good possibility it has trouble with susceptibility. Now that I've said that these two problems generally go together, let me show you some exceptions to that general statement. Let's say we've got a circuit board which has some analog circuitry on one part, which is susceptible, and high-speed digital circuits on another part of the board, which is causing emissions. Let's say we do a little rounding of the clock edge of the digital circuitry, reducing some of the high-frequency energy. There's a good chance that's going to bring down the emissions without having, of course, any effect on the susceptibility of the analog circuit. These are two different circuits, and we did something to improve one but not the other. So if they're both within the same system, they're both on the same circuit board, but they're clearly two different circuits. So we don't expect the emissions and susceptibility of the two different circuits to be related. But on the other hand, let's say we have it like this. The analog circuits are susceptible because of high-frequency noise picked up by the attached cable to the circuit board. Radiation is picked up by the cable, conducted then over to the analog circuits. And maybe it's high frequency, but if it's rectified, then it possibly could be low enough frequency to interfere with the circuitry. On the other hand, let's say the digital circuits are using that same cable as a transmitting antenna. So now both circuits are using the same antenna, one to transmit, one to receive. Well, obviously, if we could disconnect that cable, that may not be a practical solution, but just as an example, if we disconnected that cable, we would improve both. We would reduce the emissions and we would reduce the susceptibility. Even though they're two different circuits, they share a common antenna that leads to our problem. So there again, by fixing that one antenna, maybe by shielding the unintentional antenna, by shielding the cable, we can reduce the emissions or the susceptibility. So sometimes these two problems, emission and susceptibility, are not related, and sometimes they are directly related. It all depends. Now, let me give an example where fixing one worsens the other. Let's say we have a digital clock signal that is causing high-frequency emissions. Let's say we lower the clock voltage from 5 volts to 3.3 volts. If we lower the clock voltage, there's a very good chance we will reduce the emissions produced by that particular circuit. But what do we do to the susceptibility? Well, now we have a noise margin that is less at 3.3 volts. We've reduced the noise margin, so we probably have increased the susceptibility by using that technique. That's a good reason why we need to understand these electromagnetic compatibility issues. We need to know that when we do something, if it's reducing emissions, but at the same time it's increasing susceptibility, that may not be a very good solution for us in the long run. So particularly if we're not aware that the susceptibility has been increased, that could be a serious matter. So yes, generally speaking, what is good to reduce susceptibility, to improve the immunity, as people like to say it nowadays. I like to talk about it in a more positive manner, talk about how immune something is rather than talking about how susceptible it is. Well, either way, it's still the same issue. But we'd like to realize that most of the good techniques we're going to talk about for reducing susceptibility, very likely many of those techniques will be effective to reduce the emissions. All right, as far as the 4 basic noise coupling mechanisms, here they are. We can have unintentional noise conducted. This is usually going to be on some kind of wires. But a conductor. I worked on some problems for the Navy some years ago where they had sonar devices in several thousand feet of water, and the casing around the sonar device would occasionally get cracked, and at high hydrostatic pressure would force a little salt water inside the casing. Then it'd wind up with an unintentional saltwater contact internally. Now this is something that usually developed over a period of maybe weeks or months, so it was so slow in developing that it was difficult to really know just when it happened. But in this case, that's an example of a conductively coupled problem caused by a conductor. It was not an unintentional current flowing on a wire, though. It was an unintentional current flowing through a saltwater connection. Battery electrolyte sometimes causes conduction problems that we might not be anticipating. So conductively coupled. That is our most commonly encountered problem of the four. Then we can have electrical energy passing through the air in the form of electric fields, electric field coupling, or we'll sometimes call that capacitive coupling, mutual capacitive coupling. We can also have currents generating magnetic fields in the air, magnetic energy coupling. We'll also call that mutual inductive coupling. And a fourth possibility is electromagnetic waves flowing or propagating through space. Most of this session is concerned with these four coupling mechanisms, trying to understand a little better the physics behind these processes. If we know exactly how these four processes occur, what does it take to create them? What does it take to generate a magnetic field? What does it take to receive a magnetic field? Well, then of course we be careful not to do those things, and we can avoid a magnetic noise problem. So we want to understand the physics behind the four coupling mechanisms. That's the main goal of this session. Let's take a look at current through a coil. If we have low frequency current through a coil, what we expect to produce is a magnetic field in the vicinity of that coil, a localized stored magnetic energy. The energy doesn't go anywhere. If you reduce the current through this coil, you can recover this energy back into the circuit. So it's a stored magnetic energy. Now I do have to admit this is a concept or a model. We talk about fringing magnetic flux around this coil. That's just our way of representing that somehow there's energy stored there. Other people would like to represent it other ways, maybe, but we're going to use concepts of electric and magnetic fields. They seem to be fairly useful in explaining how these problems occur. So what happens at low frequency is we have stored magnetic energy. Now supposing we increase the frequency of the current through the coil up to a frequency such that the wavelength of the frequency, the wavelength lambda, becomes comparable to the dimensions of the coil. Then what's going to happen is we're going to get some electromagnetic energy propagating off of the coil. This is a flowing, transmitting electromagnetic energy. It's not stored. It's not stationary. It does not stay in one location. This is a different problem. The far field electromagnetic wave as compared to the near field stored magnetic energy. Two totally different situations, or at least significantly different situations. I realize the term electromagnetic, it has the word magnetic in it, but we want to think of this as a different phenomenon. Now at high frequency, you see you have both. You have some magnetic stored energy that stays near the coil, and you have some energy that's transmitted in the form of an electromagnetic wave out away from the coil. At low frequency, at a frequency where the coil is very short electrically, very small compared to a wavelength, at low frequency then we have just primarily the magnetic stored energy. We don't have the electromagnetic energy. Now we could also consider another example. Let's say we have a pair of capacitor plates with an AC source powering them. We're going to get an electric field between the plates as the charges oscillate between positive and negative between the plates. An electric field. So we'll have some stored electric energy between the plates at low frequency. And that's basically about all we'll have. As we increase the frequency to where we get to a wavelength that is comparable to the spacing between the plates, then at high frequency we're going to get an electromagnetic wave coming off as well. So similar to what we had a moment ago with the coil. With the coil, at high frequency we had stored magnetic energy and stored or radiated electromagnetic wave. Now with a dielectric or a dipole-like structure such as the capacitor, we have stored electric energy and at high frequency radiated electromagnetic wave. So we have four possibilities for coupling. The noise coupling mechanisms, it could be conductively coupled, could be electromagnetic wave, could be a magnetic field, could be an electric field. And again, the magnetic field we are sometimes going to call a mutual inductance, and the electric field coupling we will sometimes call mutual capacitance. Kind of depends on whether we're thinking from the field theory point of view or whether we're thinking from the circuit's point of view, which way we describe this. Now, these so-called noise coupling mechanisms, they're not new to us. These are the same methods by which we will couple signals, right? We send a signal on a twisted pair. What coupling process is being used? Well, obviously a conductive coupling. We run a signal down an optical fiber. That's electromagnetic wave coupling using a dielectric waveguide. We run a signal through a transformer from the primary side to the secondary side. We have probably, we're intending to have magnetic field coupling between the two windings. But at the same time, we probably have a little bit of our signal capacitively coupled from primary to secondary. So we may have desirable magnetic coupling between the coils, between the windings, and undesirable capacitive coupling between the windings. So again, all of these mechanisms we're talking about, these four are very familiar to us. We use one of these four anytime we send electrical energy from one location to another. So again, what I'm stressing to you is we don't have 200 different noise problems. All of our noise problems can be divided conveniently into one or more of these four possibilities. So there really are only 4 noise problems that we've got to be able to identify and fix. That's a very good situation. That's a lot simpler than we might expect it to be. So now let's take a look at each one of these coupling mechanisms, try to learn more about them, what it takes for them to occur. If we know how they occur, that means we know what to look for when we're trying to identify that particular problem. Conductively coupled noise, often it is called common impedance coupling, a very good term. What that means is when two currents share or flow through the same impedance, there's a very good chance that they may be interfering with one another. So when you see two currents sharing the same circuit or a part of a circuit, a chance we may have common impedance coupling, conductive coupling. The level of the interference may not be enough to be noticeable, so we may get away with that sometimes, but generally two currents sharing the same impedance is something we should be a flag for us to be concerned about that. What does this conductive coupling require in the way of a hardware situation? It requires 2 or more conductive contacts between the two circuits. To have a conductive problem, we must have a conductor that carries the current out someplace we didn't really intend for it to go. And then, remember what we said about all currents, they have to return back to their source. So we need another conductive path to return the current back to its source. Now, sometimes we have multiple paths out and multiple paths back. Sometimes we have more than 2. But we need a minimum of 2 conductors to have a conductively coupled problem. Now, you could say, well, what if we have one conductive path out, but instead of a second conductive path back, what if we have a capacitive connection that returns the current back to its source? Yes, we have that very often, but we're going to call that electric field coupling. This unintentional capacitance between the two circuits, that'll be the dominating factor here. And so this will be described as a mutual capacitance, that is an electric field coupling problem, whereas this is purely a conductively coupled problem. What are the 2 wires that we typically have to worry about that are going to bring in or out this unwanted conductive coupling? Well, DC power is the #1 pair of wires to be concerned about. All electronic circuits need some kind of DC power to operate off of. Those 2 wires that bring the DC current in and out of our circuit, those same 2 wires can bring in the unintentional conductive noise. A lot of times we're running things off of AC power. That's how we get the DC power. So it may all start with unwanted conductive noise coming in on the 2-conductor or 3 or 4-conductor AC line. So power connections, particularly DC, but power connections are our prime concern for unwanted conductive noise. Of course, we can bring in conductive noise on a signal pair, so we worry some about that. But any metallic connections, usually they're for electrical purposes, but you even got to watch occasionally mechanical connections. You may have one electrical connection and a second mechanical connection that is conductive, and the unintentional current might use those two contacts. So any two conductive connections are possible sources or paths for conductively coupled noise. Let's look at this example. We have two integrated circuit chips sharing the same DC supply. Maybe they're digital circuits. Let's assume they are digital, so this might be a 5 volt or a 3.3 volt, or, well, I guess nowadays we're using all sorts of voltages, 1.8 volts and so forth. Let's say IC chip number 2 is the one that is drawing the bulk of the current. It's doing most of the switching. And so we're concerned about when IC number 2 switches, what about the voltage that is developed along the DC power distribution path? That fluctuating voltage means that the DC voltage at the load is going to fluctuate, which we don't want that to happen. Let's first talk about what these two elements in the equivalent circuit represent. In session number 1, we talked about how individual conductors have resistance. So this conductor has resistance, this conductor has resistance. The output of the DC supply maybe has a little resistance. In this equivalent circuit, that resistor right there represents the total resistance of this loop right here. The total resistance lumped into one value. What does that self-inductance represent? Well, that's not the self-inductance of the top wire. An individual wire does not complete a loop. It does not have self-inductance. But in this case, we can see there is a complete loop here. And you might have to say, well, exactly where is it closed? But we'll assume this dimension is small relative to the rest of this. It's not quite drawn to scale. So these 2 points are almost together. So we have pretty well defined a complete loop here. That loop has some self-inductance. Let's say the resistance is about 1/10 of an ohm. Let's say the self-inductance is 100 nanohenries. Remember, we said a loop 3 inches in diameter would be several hundred nanohenries. So this is probably going to be in that range, 100 nanohenries or more. Let's say that current I2 is 100 milliamps peak, and it's switching in a time interval of 10 nanoseconds. So we'll say that's our value for dIdt. Delta I is 100 milliamps, and delta T is 100 nanoseconds. So we put those values for R, I, and L in here, and what we're going to get is a resistive drop of 10 millivolts and a reactive drop, a drop due to the wiring inductance of 1,000 millivolts. That gives us a pretty good idea of the relative scale of this problem. For most fast switching type circuits, digital type circuits, the LDIDT, the inductive voltage drop, usually dominates by a long shot the RI, the resistive drop. And that's exactly what happens here. So how do we reduce this problem? Well, we want to do something about this loop area. We don't necessarily need larger conductors. If the resistance was a problem, if the resistive drop dominated, then we'd need either shorter wires or larger diameter wires. But that's not the problem. It's inductive. We've got plenty of copper. The trouble is we don't have it in the right place. We need to move this conductor closer and that conductor closer. Decrease the separation between the conductors. Also decrease their length if that's possible. Probably not possible here. So we'll move them closer together. When you have an inductance problem, it's usually an issue of rearranging the metal, placing the metal in a better location. If you've got two conductors that are too far apart, we just simply put them closer together. It doesn't do as much good to make the conductors larger. If they're far apart and we make them bigger, it'll help some, but that'll be a lot of waste of money on the copper. And we just want to take the metal we already have, move it closer together. That'll increase the capacitance, which decreases the inductance, and that'll be the solution we want to use. So when we have an inductance problem, we rearrange or reposition the metal that we are already planning on using. Like on a circuit board, you got too much inductance in the trace pair on a circuit board. We don't necessarily need to go from a 6 mil wide trace to a 20 mil wide trace. That would help maybe, but we need to look at the spacing between the traces, move the traces closer together. On the other hand, if it's a resistance problem, moving the wires around doesn't change the resistance. It's the size of the wire and the length of the wire that determines the resistance. In that case, we're just going to have to go with a little bit bigger wire to lower the resistance. What do we need for electromagnetic wave coupling? Well, in order to have an antenna, in order to have something to transmit electromagnetic waves, it has to be of some reasonable length. Length compared to what? Well, compared to a wavelength. If the length of the cable that we're thinking of as possibly being an antenna, if that length is much less than a wavelength, then the distance to the far field, the distance to where the electromagnetic wave dominates over any other effects, that distance is approximately a wavelength. So for a very small antenna, electrically small antenna, the distance that takes you out of the near field, where the electric and magnetic fields dominate, into the far field, where the electromagnetic wave dominates, that distance for an electrically small antenna is about a wavelength. If the antenna is comparable to or larger than a wavelength, then the distance to the far field turns out to be twice the length of the antenna squared divided by the wavelength, which translates into many wavelengths. What we really want to know here is, what's the minimum distance to be in the far field, where the electromagnetic wave dominates over all of the other effects? The minimum distance is at least a wavelength. Sometimes you need to be many wavelengths to be in the far field. A lot of times you read in books that the distance to the far field is a wavelength over 2 pi, roughly 1/6 of a wavelength. You've got to realize that's for an antenna of 0 dimension, an infinitesimal, 0-length antenna, which we don't really have. In reality, antennas are some significant physical length, and so the distance to the far field is always greater than a wavelength over 2 pi, and usually it's even greater than a wavelength, but that's the minimum condition. So in order to have electromagnetic wave coupling, a necessary requirement is we have to have a distance from where the electromagnetic wave is launched to where we receive that wave. The distance has to be greater than 1 wavelength. What we're going to find is a lot of times when you check this out, this condition is not met. If that condition is not met, then we don't have electromagnetic wave. Then we're in the near field and some other effect will be dominating. Let's try this on an example. Let's say we have our kitchen mixer sitting about a meter away from an AM radio that's battery powered. And every time we turn the mixer on, we get noise over here on the radio. So we know where the source of the noise is located. It's that kitchen mixer. And we know the circuit that is susceptible. It's the AM radio. But we need to figure out what's the coupling mechanism. Now remember, we've got 4 possibilities. And what we're trying to do here is we're trying to figure out which are reasonable, which are likely in this situation. Let's just run down the list. Conductively coupled. To be conductively coupled, we required 2 or more metal contacts between the noise source and the susceptible circuit. In this case, we don't have any contacts, battery powered. So conductive coupling is not a possibility. It's not even on the list. We don't even want to consider it. What about electromagnetic wave? Electromagnetic wave, we required a distance greater than a wavelength. All right, do we meet that condition here? The distance is 1 meter. What's the wavelength? Well, we said we're going to get the wavelength if we know the frequency. You take frequency times wavelength, that's the phase velocity in the medium. Okay, so if we know frequency and velocity, we can get wavelength. Well, what's the frequency of this noise problem? See, that can be a little bit tricky. Sometimes the frequency you observe, in this case what we hear coming out of the radio as noise, that's an audible frequency, probably around 1 kilohertz or so, or well, actually quite a few frequencies. The frequency we hear in this case is not the frequency of the coupling, is it? The frequency of the coupling is the RF frequency. The noise is coming in somewhere in the AM band, probably all across the AM band, which runs from about 540 kilohertz to about 1.6 megahertz. So I would say the average frequency of the coupling is around 1 megahertz. So that's the frequency of the coupling, but that's not the frequency we hear. We hear the modulation that's on the coupling frequency. So let's say the frequency is 1 megahertz. If we work out the wavelength, we'll get the wavelength to be about 300 meters. And what's the distance? The distance is 1 meter. 1 meter is not greater than 300 meters. So this cannot be electromagnetic wave coupling. All right, it seems like we're making good progress here, and I think we are. We started out with 4 possible coupling mechanisms. We got conductive coupling, electromagnetic wave coupling. Both of those we've eliminated as possibilities here. All we've got left is magnetic field coupling and electric field coupling. So now we need to figure out which one of those two is likely dominating this problem. Now we haven't talked much yet about electric and magnetic fields and how they're generated, so maybe we don't have quite the background to finish this problem, but we'll do a little more with it. Let's assume the noise is coming in through the antenna on the radio. That's probably a pretty good assumption. If the antenna is a wire whip antenna, a monopole type antenna like the FM band uses, if that's the type of antenna, then we know the coupling mechanism is going to be electric field coupling, because a whip antenna only picks up electric fields. It does not easily or significantly, well, theoretically it responds to the magnetic field. Practically speaking, it doesn't. Practically speaking, it really only responds to the electric field. So if I know the type of antenna used for the AM band, that could be a clue as to what the coupling process is. On the other hand, a lot of times on a portable radio, the AM band uses a ferrite rod with a coil wrapped on it. But it's usually quite a few turns of wire. So you'd think with a coil that the obvious coupling mechanism would be magnetic coupling. Well, it could be. A coil does pick up a magnetic field. See, loop areas, which is what a coil has loop area. Loop area allows you to pick up a magnetic field. But also, a multi-turn coil has a lot of surface area to the wiring. Wire surface area allows us to pick up electric fields. So actually, the ferrite rod antenna would be a little harder to decipher. We'd need probably more information to decide really what the problem is. But possibly by looking at the antenna, we could determine the coupling mechanism. Now also, we haven't said anything about how does the mixer generate noise? Some kind of arcing contacts, right? When contacts arc, do they generate mostly magnetic fields or mostly electric fields? What does the physics of the arcing process say? We probably ought to look into that a little bit if we've got real interest in this problem. We study the physics of arcing, maybe we'll get a good clue about whether we ought to worry about electric fields mostly or magnetic fields. So you see, there's a lot more information to take advantage of here. I don't know that we're quite all prepared to use it yet. I would expect the problem we're describing most of the time turns out to be electric field coupling. But let's go on here. We need to work a little bit more and take a look at what produces electric fields and magnetic fields and understand those processes a little bit better. Magnetic fields, particularly time-changing magnetic fields. What does it take to produce such a situation? Well, currents, particularly time-changing currents, produce time-changing magnetic fields. There's a very simple linkage between those two. But we want to be aware of it. We want to take advantage of it. Just make sure we're familiar with it. Now, what produces electric fields? Well, unneutralized charges, positive and negative charges, produce electric fields. But how do you get positive charge on one wire, negative charge on the other wire? Usually what you do is you apply a voltage difference to the wires. The voltage difference separates the charges. The charges produce the electric field. So I just leave out the middle step. I say time-varying voltages produce time-varying electric fields. Again, we're looking for a very simple association between something that's happening in the wiring and something that's happening around the wiring. Currents on the wires produce magnetic fields around the wires. Voltage differences between the wires produce electric fields between the wires. There's a very good way to diagnose a problem by using this approach. Supposing, in fact, let's switch over and use this for a moment. This is the power cord going to my scope over here on the side. But let's say what I notice when the scope is turned on, the power cord is energized, that when I move this power cord near a piece of equipment, let's say we got equipment sitting down below me here. If I move the equipment or the power cord near the equipment, the noise level increases. All right, that tells me it's probably going through the air because it's distance related. When noise is related to distance between one object and another, that's a good suggestion, a good clue that it's a problem going through the air, that it's not conductively coupled. So I'm going to throw that one out, that one of the four. Let's also say the frequency of this noise is 60 hertz, as I might expect the power line to generate. 60 hertz, the wavelength is 3,000 miles approximately. To be electromagnetic wave, I would need a distance between the source and the susceptible circuit, a distance greater than a wavelength, which clearly can't happen here. Anytime the frequency is below a few 100 kilohertz, it's not very likely it's going to be electromagnetic wave because you need such a large distance. So I've eliminated now conductive coupling and magnetic field coupling, or conductive and electromagnetic wave coupling. The two that are left are electric fields and magnetic fields. How do I decide which one of these two effects is being produced by this cable? Well, if I were to turn my scope off, that is, disconnect the load that's connected to this cable, disconnect the load, let's see what happens. Say I turn the scope off, I move this cable around, I notice the noise is now gone. What was the problem? It was the current producing the magnetic field around the cabling, right? The voltage you see is still present. Between the wires inside this cable, the voltage exists, the electric field is still there. So if it were an electric field coupling problem, it would still be present. But the fact that I've eliminated the current and that eliminated the problem, that says it was a magnetic field problem. So that's a way we could use, a technique we could use to diagnose the situation. And that's what's suggesting here. If you have a source and a particular cable, and this cabling is generating some kind of problem, but we don't know whether it's electric field or magnetic field. If we disconnect at the load end of the circuit, not the source, if you disconnect at the source end, we eliminate both the voltage and the current on the wiring. And all we can prove is that that wiring was the source of our problem, but we can't prove how it was the problem. If we disconnect at the load end, then we could eliminate the current and eliminate the magnetic field while keeping the voltage and the electric field. So based upon what happens when you disconnect the load, you can decide whether the problem was one of magnetic field coupling or one of electric field coupling. Now, in order to predict which is going to dominate, electric fields or magnetic fields, here might be a useful thing to look at. The time-varying voltage is related to the electric field. Time-varying current is related to the magnetic field. If we take the ratio of these two derivatives, the ratio has the units of ohms. It's not impedance. Impedance is a frequency domain concept. And here we're working in the time domain. But the units, nonetheless, are ohms. So the ohms number, whether it's a large value or a small value, might be a very good clue to indicate whether the electric field dominates or the magnetic field dominates. Now, here's what I'm going to do. I started out with arbitrary wave shapes represented by voltage and current derivatives. Let's assume for the moment that we're dealing with a cable that has only sinusoidal waves, a sinusoidal voltage and a sinusoidal current. In that situation, we can basically go over into the frequency domain and just look at the ratio of voltage to current, which is now impedance. We can only do this for the sinusoidal situation. We can't do this for arbitrary pulse-type wave shapes. But for a moment, assume sine waves on the cable. Now, let's say this cable that's generating noise troubles, let's say in one case it's got a 10-volt signal on it, and the signal current is 1 amp. Signal is 10 volts and 1 amp. But that signal is causing a noise problem, coupling something through the air. Well, because of the large current relative to the voltage, 1 amp I think is large relative to 10 volts, that goes along with an ohms number of 10 ohms. A low ohms number means generally a lot of current relative to the voltage. This number suggests probably, not for certain, but probably a magnetic field coupling problem. On the other hand, if this cable causing noise had 1,000 volts and 1 amp of current, meaning an ohms number of 1,000 ohms, then I would be more suspicious of the high voltage causing an electric field problem. I wouldn't be certain, but it would just be a probable indication. So the ohms number is a good indication as to whether it's going to be magnetic field or electric field. Now, what value for the ohms number should we use as a dividing line between electric fields and magnetic fields? Well, I'm going to use 377 ohms. That happens to be the characteristic impedance for a plane wave propagating through empty space. And for a plane wave in empty space, neither the electric field nor the magnetic field dominates. Both electric and magnetic fields seem to be contributing in a similar way to the effects. So, again, we don't need a number here that's accurate out to 3 decimal places. The technique that we're using here is very approximate. We're saying 10 ohms is suggesting a magnetic problem. 1,000 ohms is suggesting an electric field problem. Something between 200, 300, 400 ohms, that's in between. We're not sure. I'm going to use 377 ohms simply because that's a number that I remember. And it happens to be in about the right range. A few hundred ohms is where the problem divides or switches from one difficulty to the other. All right, let's review what we're saying now. Let's go back to the general case. We've got a time-varying voltage. We've got a time-varying current. We divide the two. We look at the ratio of the two derivatives. If that ratio is much less than a few hundred ohms, we're thinking probably a magnetic problem coming from this type of source. If that ratio is much greater than a few hundred ohms, probably we're dealing with electric fields. Again, I use the word probably. This is a little bit of an estimate. It's not precise. But you see, to solve a noise problem, usually we don't take one clue or one symptom and base a complete analysis on that. We usually look at several indications. Say you've got a circuit where there appears to be considerable current compared to the voltage. Suggests magnetic field trouble. Doesn't say it has to be. But now let's combine that with an unusually large loop area for that circuit. Well, that further suggests it would be a magnetic field problem. So you see, as you take these indicators that point in particular directions, that indicate one kind of trouble or another, you take these weak indicators, you put them together, and eventually you can get a pretty strong indication of exactly what kind of problem you'll be dealing with. Now, to summarize this, we said if the coupling mechanism is conductive, one of the primary requirements is going to be two metal contacts between the noise source and the susceptible circuit. This is a very good indication. I mean, but in some sense it's not that helpful to us, because most of the time we have lots of wires connecting products together. Many wires available. That doesn't mean we have to have a conduction problem. It just means we could have, we might have. The absence of wires is the big indicator. Then we know it's not conductive. What about electromagnetic waves? What do we need for that? We need to be in the far field. We need a distance greater than a wavelength. This is a very helpful idea. Many times we're going to find when we run through the numbers, you know the frequency, you know the distance involved, you calculate the wavelength, you'll find out that this condition here is not met. When this is not met, it tells us we cannot be having an electromagnetic wave problem. What about magnetic fields and electric fields? If the ohms number is small, more likely magnetic fields, and if the ohms number of the noise generating source, if that ohms number is large, more likely electric fields. And the way you get the ohms number is you take the ratio of the voltage derivative divided by the current derivative. This is the voltage and current of the circuit, the switching circuit, that's causing us the problem. Of course, we don't want to be looking at voltages and currents that are not associated with the problem. If we know the circuit which is causing the problem, from which the noise is emanating, then if we know something about the rate of change of voltage and current in that circuit, then we can use this number to give us an idea what the problem might be. All right, now we'll just do a couple of examples that again are not in your notes, but I wouldn't bother to write any of these down. Just maybe listen to what we talk about here. That'll probably be good enough. One problem I worked on several years ago involved noise generated by an electric furnace, a large electric furnace, and it was causing noise in nearby thermocouple lines. The thermocouple lines were measuring the temperature at various points in this process. Now, the characteristic features that we had for this particular situation made diagnosing the noise problem in this case pretty easy. The electric furnace ran off of three-phase 480 volts AC. That seems like a pretty high voltage. But when you realize that the current was 2,000 amps, then the voltage looks pretty insignificant compared to 2,000 amps. The frequency was not exactly sinusoidal, but pretty close, 60 hertz. So we don't have to use the derivative anymore. Now we can just use the ratio of voltage to current. We do that. The ohms number is a fraction of an ohm, much less than 377 ohms. Therefore, a very strong indication that this is a magnetic field problem. And that's exactly what it was. So what do we have to do? We have to go out there and the thermocouple lines that are susceptible, we have to trace out every inch of that thermocouple wiring, try to find where the wiring is not tightly twisted together. And sometimes it would be at a terminal block where the wiring would be hooked up to a terminal block, they'd be spread out a little bit, there would be a loop area, and that's where, in a matter of a few square inches, the AC magnetic field was coupling in, causing a problem. So we know if the dominant problem is magnetic fields, the best solution for that problem is don't give the magnetic field any loop area to couple to. Trace through that susceptible circuit, find those loop areas, reduce those loop areas, squeeze out that loop area, and that'll be a good way to fix that problem. That's exactly what we had to do. It was a tedious process of tracking down the wiring, following it all along its path, just to find all those loop areas. But that's the thing that needed to be done. There was no way to get rid of the source in this situation, so we had to fix it on the susceptible end. Another problem. Let's say we've got a cell phone that when somebody brings it into your hospital room and it gets near your electronic monitoring equipment, it causes the equipment to be upset in some way. Well, the cell phone transmits around 900 megahertz. Of course, the newer versions are coming out maybe at around 1800, but several hundred megahertz is all we really need to know here. Very high frequency, but no metal contact between the cell phone and the hospital electronics. So this pretty much indicates that we're dealing with a short wavelength, a wavelength that is short relative to the distance involved, so pretty clearly an electromagnetic wave coupling problem. Was the hospital electronics, maybe which was designed and built 15, 20 years ago, did they have in mind then all of these literally thousands of RF transmitters that we have nowadays? No, I don't think they had those in mind at that time. I don't believe that electronics was designed to keep out those RF frequencies. So, and until that equipment's replaced and updated or whatever, we're just going to have to keep those cell phones and other RF generators a little farther away from that kind of susceptible equipment. But again, this is a pretty easy one to diagnose. It's the frequencies and dimensions are such that it's pretty clearly electromagnetic wave coupling. And probably just keeping the products separated is the simplest solution in this case. Let's try another one. Let's say we've got noise coming from a fluorescent light. But now let's make sure we know that the noise is coming from the fluorescent light, the fluorescent tube, not the ballast if it's the old style tube or fluorescent light. The ballast might be a magnetic field problem, but the tube itself is different. The tube coupling through the air is at, we'll say, kilohertz frequencies. Of course, there's all sorts of frequencies coming out of this tube, literally to daylight. But let's say we're concerned about the lower frequency noise that we're picking up, something in the, maybe it's 60, 120 hertz, but maybe it also goes up to a few kilohertz. So it's low frequency. But the tube operates at fairly high voltage, 1,000 volts or so, and very low current, a milliamp or so. So it's high voltage, low current, low frequency. That device should probably produce in the air mostly electric field. Yes, theoretically it produces magnetic field, but the tube itself mostly is going to produce electric fields at the low frequencies. Now here's a tough one, electrostatic discharge. Electrostatic discharge can be about any kind of problem. You can have a direct contact between the discharge and, say, the pin of a connector, and you can simply dump or force current directly, conductively, right into the circuit. If it's a conduction problem, we're going to fix it with a filter. The only way we fix conductive troubles is by filtering. On the other hand, electrostatic discharge, you have frequencies to go 200, 300, 400 megahertz. Those are fairly high frequencies, short wavelength. You could have truly electromagnetic waves propagating through the air and somehow being received by the susceptible circuit. At the same time, you've got a rapidly discharging voltage, rapidly changing voltage. That produces electric fields. We've got considerable amount of current. I think for some people it's surprising. Electrostatic discharge, there might be 40 amps in a nanosecond or less, pretty high DIDT, and quite a good possibility of magnetic fields. So in this situation, if all we know is that electrostatic discharge is, causing trouble with a particular piece of hardware, I don't think we're going to be able to diagnose the problem. We're going to need some more information. Without more specific details, we'll not be able to home in on this particular problem. I think maybe we'll stop there and just review for you now. We've got 4 coupling mechanisms. We've got conductively coupled noise, requires direct metal contact, usually 2 metal contacts or more. We've got electromagnetic waves. You have to be in the far field for that effect to dominate. That's a distance greater than a wavelength. And then we have magnetic fields, which are generated by currents, and we have electric fields, which are generated by voltage differences. Those are our 4 coupling mechanisms. If we understand those 4 and know what to look for, we can then diagnose and better fix our noise problems. This concludes session 2.